Welcome to the GeoMethod channel. Today we are solving another interesting geometry problem. Here is the original problem. Begin with the givens only and keep the board quiet. The first given is segment AB has length 3. Add the second secant length next. Segment AD also has length 3, so the two marked pieces from A start with the same distance. Now mark the short outside secant piece. Segment CD has length 1, and that small piece will help build the whole secant in a moment. At point E, segment CE is tangent to the circle. That tangent fact is essential because the tangent-secant theorem will come from the external point C. Angle B is a right angle, so triangle ABC is a right triangle. That tells us the large triangle can later feed a Pythagorean step. Now combine the two secant pieces. Since segment AD has length 3 and segment CD has length 1, the whole secant segment CA has length 4. We are preparing the tangent-secant theorem. From an external point, the tangent length squared equals the outside secant piece times the whole secant. The helper chords help us earn that fact, instead of simply quoting it. Mark the shared arc, DE. This arc is what lets us compare angles and build the similarity proof behind the tangent-secant theorem. These two marked angles are equal, and that is the hinge of the theorem proof. Watch the highlight alternate between the left triangle DEC and the right triangle EAC. Those are the two triangles in the similarity statement. Now watch the ratio chase. First, the left side lights up as segment CE over segment CD. Then the right side lights up as segment CA over segment CE with the same two colors. Multiplying across gives the tangent-secant equation. Segment CE squared equals segment CD times segment CA. Now use the known lengths. Segment CD has length 1 and segment CA has length 4, so segment CE squared becomes 1 times 4. At this point, the tangent-secant theorem has done its job. Segment CE squared is 4. Keep only that earned equation on the board. Solve for segment CE. Taking the positive square root turns the theorem result into a concrete segment length. Use the large right triangle ABC. With segment AC equal to 4 and segment AB equal to 3, the last side comes from the Pythagorean theorem. Simplify the known squares. The fixed side lengths become the numeric equation segment BC squared plus 9 equals 16. Move 9 to the other side. Now isolate segment BC squared before taking the square root. Simplify the right-hand side. The large triangle computation is now reduced to segment BC squared equals 7. Resolve the full base length segment BC. Take the positive square root so the remaining base is known exactly. We already know the whole segment BC and the tangent piece CE. Since E lies between B and C, the leftover part is segment BE. Subtract segment CE from both sides to isolate segment BE. Written cleanly, that says segment BE equals segment BC minus segment CE. Now put in the two values we already found. Segment BE becomes root 7 minus 2. Keep that exact length in view. It will be copied into the smaller construction in a moment. Carry that exact value forward, because segment BE will soon reappear as another side of the figure. Draw segment OE from the center to the tangency point. A radius to a tangent is perpendicular, so this is the first construction that turns the picture into something more useful. Keep both perpendicular facts in view. Segment OE is perpendicular to the tangent, and segment AB is also perpendicular to that same tangent direction. Because both lines are perpendicular to the same line, they are parallel. So segment OE is parallel to segment AB. Now drop segment OF perpendicular to segment AB. This creates the second side of the small auxiliary box and also introduces the future triangle AFO. Since segment OF is perpendicular to segment AB and segment CE is also perpendicular to segment AB, those two lines are parallel as well. That completes the rectangle structure. Mark the radius label next. Segments OA and OE are radii of the same circle, so both carry the unknown radius r. These right angles turn OFBE into a rectangle. That matters because a rectangle lets us transfer lengths without new computation. Take a brief look at the finished rectangle before moving on. It is the bridge between the old exact length BE and the new small right triangle. Use opposite sides of rectangle OFBE. OF equals BE and BF equals OE. This is the transfer step that carries one known length and one radius into the small triangle. Now use the rectangle. In rectangle OFBE, opposite sides are equal, so segment OF equals segment BE. Replace segment BE with the exact value we already found. Segment OF now has the concrete length root 7 minus 2. Keep that horizontal leg in mind. It will become one of the two legs in the final small triangle. The second rectangle transfer is segment BF equals segment OE. This copies a radius length onto the baseline. But segment OE is a radius, so segment BF equals radius r. That gives us the second labeled piece we need on segment AB. Now look back at the whole segment AB, whose total length is 3. We are about to split that whole segment into two parts. Since segment AB is the whole segment and segment BF is the right-hand piece, the leftover left-hand piece is segment AF. Carry segment OF into triangle AFO as the fixed horizontal leg of the small triangle. The other short piece near B is segment BF equals radius r. Keeping that in view makes the subtraction on AB easy to read. Subtract segment BF from segment AB, and you get segment AF equals 3 minus radius r. Now the small triangle is completely labeled. At this point, the whole problem has been reduced to triangle AFO. All of the earlier geometry was only preparation for this one small right triangle. Apply the Pythagorean theorem to triangle AFO. Its legs are already labeled, and its hypotenuse is a radius. Once the equation is written, the remaining job is algebra. Start by expanding both squares carefully. After expansion, every term is visible on one line. This is the full algebraic form before simplification. Now combine the constants while keeping the radical terms separate. That makes the structure of the equation easier to read. This is the simplified equation we need for the last step. The geometry is finished, and only algebra remains. Read this line carefully. Every geometric fact from the construction has already been absorbed into this one equation. Carry this cleaned equation into the final step. From here on, solving for the radius is plain algebra. Cancel radius r squared from both sides. That removes the quadratic part and leaves a linear equation. So we are left with 20 minus 4 root 7 minus 6 radius r equals 0. Move the radius term to the other side. Now the equation reads 20 minus 4 root 7 equals 6 radius r. Rewrite it as 6 radius r equals 20 minus 4 root 7. Divide both sides by 2. That simplifies to 3 radius r equals 10 minus 2 root 7. Finally, divide by 3. The exact radius is 10 minus 2 root 7 over 3. As a quick check, that is about 1.57. We already have the answer. Now it is worth reviewing the chain of facts that made the solution work. Next, remember the circle theorem. This is the theorem that turned the tangent segment into an equation we could solve. Then use the large right triangle. That step gives the full baseline before we split off the tangent piece. After that, we isolate the leftover piece on the baseline. This subtraction prepares the exact length used later in the small construction. After that, build the perpendicular radius structure. This is the step that turns the picture into a rectangle transfer setup. Then use the rectangle to transfer lengths. Opposite sides of the rectangle give the two equalities we need for the small triangle. Finally, solve the small right triangle. That last Pythagorean equation is the step that actually produces the radius. That is the whole route to the answer. Theorem, large triangle, transfer, small triangle, and final algebra. If you like my channel, please click the like button and subscribe to my channel and leave a comment if you have any questions.